So in the previous session, we were looking at the sampling procedure, right? Specifically for a non-band limited signal, we convert that into a band limited signal uh, by using a filter, then sample at a rate which satisfies the Nyquist rate, so that you get a guard band in the middle, so that you have some advantages related to the reconstruction filter, right? Wherein you don't have to go for a very higher order filter design, right? You can manage with the lower order because of the presence of what is called as the guard band in the middle. Okay, so continuing from here, next we are going to look at what is called as the practical aspects of the sampling. So the next topic is aspects. So far, whenever we use the word sampling, this is we were trying to refer to uh, the ideal sampler. What do you mean by ideal sampler? Let's look at that now. So I'll write one point here. So far, the, the sampling circuit used was ideal. Okay, this is ideal in nature. So, what do you mean by the ideal behavior of sampling circuit? Recall, we had a signal, we used impulse train for sampling a continuous signal to get a discrete version of that or the samples of that. Now, from the basics of the delta functions or the impulse functions, in case of a continuous signal, the delta function has the following characteristics. The first thing is that what is if you are able to recall, try to recall that what should be the width of that uh, delta function. It exists at say t equal to 0. Let's try to write that for our reference so that this is useful later. Okay, so if I try to say that I'm using this function for sampling, right? So one of the sample, let's try to write, and this is the function. Okay, so I'll write this. It's at t equal to 0, it exists, and this is delta of t, right? So this should exist at t equal to 0, right? So exists at t equal to 0. Now, anyway, I normally we say whenever we try to define this, right? This is how it the definition of delta of t, right? Delta of t is equal to 1, right? At t equal to 0, this is 0 else. This is not just the definition. In addition to this, this should also satisfy one more condition, that is and minus infinity to plus infinity delta of t dt is equal to 1. So all together, this is the definition. Okay, so this is the definition of the delta function, that is delta of t. Now use these two to understand what exactly we mean by the ideal nature, because this is the function I'm using. I'm repeating this at different values of time to sample, right? So because of that, uh, Again, later on, I'll ask another question. Is it possible to create this signal as it? Right. Before that, I need some other answer saying that, right? What does this mean? When I say delta of t is 1 at t equal to 0 and integration minus infinity to infinity is equal to 1, right? Means so signal should exist only at t equal to 0 in the sense it's a continuous function, correct? So you see this is continuous domain, right? Which means if the function is there even slightly after 0 or slightly before 0, that needs to be justified, that needs to be defined. So here they say that signal is only at t equal to 0. It means it is not, this function is not there at t equal to 0.00000001. It is not there. Function is not there. Function's value is 0. It is even not there on the other side of 0. That is minus 0.00000001. At that point also it is not clearly defining that it is 1 at t equal to 0, 0 elsewhere. Any other t you take, it's there. So I will also write that t is continuous. It's a continuous function. Okay, so because of that, now I should be able to extract what do you mean by this is actually an ideal function. This practically implementing is not possible, right? So uh, anyway, I told the answer. Practically you cannot generate this because of some reasons. Now can you guess what reasons it could be? So I try to define delta function. I also mentioned that minus infinity to infinity, integration of that function is 1, right? Anyway, we know that integration of a function results in the area of under the curve. So I know that this area under this delta function should be equal to 1. So that's what they say, right? Function should have value 1 at t equal to 0 and the area under the curve also should be expected to be 1. But the function does not exist anywhere other than the point t equal to 0. So how do you get this? How do you imagine such a function? Right? Let's try to understand what is the delta function first, then we'll come back, right? Maybe, right? But before that, my question, what is the width of the pulse? So this is, take, consider this to be a pulse, like, because unless and until you have a pulse, you cannot sample, correct? So now my question is, what is the width of the pulse? Width of the pulse. Width means along the time axis, I should have, see, if I define like this, right? This is the time axis. This is the width of the pulse. This is the height of the pulse. Okay. Height, this is the width. So according to this representation, if I consider delta of t as my sampler function, that means the function which is used to sample any other continuous function, right? How does it match to our requirement? That's another version of my question, right? So what is this delta function, right? What is see, there is another version of the same question. So if I try to write like this is a continuous delta function. Okay, so this is, I can write delta of t versus time at t equal to 0. Equivalently, even on the continuous, not continuous, sorry, discrete domain, I have another function that is delta of n. You see, this is, there is a difference between the representation. This is delta of n. Again, that exists at 0. But you see, there is a difference, right? There is difference. There is an arrow mark specifically for delta of t, right? So not my current discussion is only about delta t, not on delta n, right? Delta n is very simple. Delta n definition has no integration, no summation over there, right? If you remember the definition which I have written here, right, above whatever you see, it's only for delta function. Delta function has this additional part, minus infinity to infinity delta t dt should be equal to 1. That condition is not there for the discrete because of certain reasons, right? Because this delta t is very unique, right? And it has a lot of features embedded in that, right? Then let's try to understand that first, then we'll go back to the communication aspects where we will see how to use this practically, right? Once you understand what are the concepts I'm talking about. It becomes more easy for you to analyze and discuss further about the sampling process. Okay, so if you can, 1 second. All right. Okay. So this was my question, right? What do you mean by this delta t? Again, there is another interesting point to understand about this arrow mark. Why do you write an arrow mark, right, for a delta function, delta t specifically, continuous delta function? Why do you write an arrow mark? What's the meaning of that? Is there any meaning in that? Do you know the answer? Recall the concepts from signals and systems. So my question is why the representation is different, though one is discrete, one is continuous. Both do the same job on both the domains, discrete or continuous time domain, right? Why there is a difference, or what is the difference between delta n and delta t? Yes, even if you can try to answer that, that's enough for me. Let's try to answer that. I'll try to give another view of this answer, because if I simply say directly, if I give you the answer, it uh, may not be appropriate. Okay, let's try to do one thing. So anyway, I understand that there is a definition. In the definition of the delta function, it has two parts. First part we understood. Delta t is 1 at this t 0, 0 else. That's fine. Again, specifically, they added another part, minus infinity to infinity, delta t dt is 1. Right? So this is the actual part of the definition of the delta t, which is not present in the delta n. Okay, now I'll consider a general function. Let me try to consider a rectangular, uh, uh, let me try to consider a rectangular function. Okay, so the function I'm trying to write should look like this. Okay, this is the time axis. Now, let me assume that this is how it looks like. This is a rectangular function. I'll say that this value, the horizontal value starting from 0, the width of this particular pulse is say delta. Okay, it's a delta. Now, in order to make this area to be equal to 1, area under the curve to be equal to 1, what should be this amplitude? What should be the height? So that the area becomes equal to 1. Width is given 1. Delta into what makes it 1? Because length into breadth, right? Length into height, whatever. So what should be this value? It's 1 by delta, correct? Yes. So that now this area becomes equal to 1, right? Now whatever, let me say this is some x of t, doesn't matter. Now you see, under this particular condition, if I try to do the integration minus infinity to plus infinity, right? What is the area under the curve? This curve function exists only from 0 to delta. So the area is 1, correct? Okay, right. This is one function which satisfies our requirement, say minus infinity to plus infinity. This function, whatever function, this is x of t dt. Now this is equal to 1, isn't it? Okay. Now let me try to modify this. So the same this thing. Okay, I'll show you what I have written so far, and I'll also show you the modification so that you understand what exactly is happening. And maybe the third step will be the one which I can directly go to the delta function. Okay, so this is my function now. Now you see, I try to reduce the delta value. The width of the pulse I try to reduce. Okay, so this is zero now, this is delta, right? So the width of the pulse, you can consider that. Okay, now the width of the pulse is how much? It's still the notation is delta, but I reduce the delta value. So this is 0, this is delta. So when the delta reduce, you can observe that in order to maintain the condition that area under the curve should be 1, the 1 by delta increased, correct? So I'll call this is some x2 of t possible, right? Versus time. So now also you can see that, right? Irrespective of which function it is, right? As the area under the curve is 1, width of the pulse reduction implies that I'll write still area equal to 1. So in this case also I can see that the area under the curve is 1. Now delta reduces implies the 1 by delta or the height of the pulse increases, correct? Now let us go to the case of okay, this is what brings us to the delta function now, right? Now if the delta tends to 0, now you tell me what happens to 1 by delta. 1 by 0, 1 by 0 is infinity, correct? So that means when I write at t equal to 0 on my time axis, I have a delta function. The what is the width here? You see, this is the delta is the width, right? So what is that? That is 0. It's there is no width actually, right? And what is the height? It goes to infinity. That's why you put an arrow mark. It goes all the way to infinity. Then you write 1 here. That is not the magnitude, that is the area under this curve. Okay, so I have a question now. Is it possible to generate this function? Using a circuit, can you generate this waveform? Right? Amplitude is infinity. Can you generate? No, that's what was my oldest question, right? Practicality of this. It's an ideal case. So this is an ideal signal. Anyway, nowhere in the world you can generate this particular function. This actually exists only in, right, only in the form of theoretical aspects. Like when you say you are dealing with the like mathematics, whenever you are building some models, right, you can use this. This is ideal case, right? So this means, right, so this is the width and this is the height, right? So because of all this is a ideal case. So I cannot generate this, right, using any sort of circuit. Amplitude infinity is not there. Okay, right. Again, so when I say width is 0, I should be this is what is the why I'm still saying that this is ideal, because if I have a pulse like this, you see, at 0, all of sudden your function should jump to an infinite value. This is infinity, and see, this width is not there at all. Immediately it should come back from infinity to 0. It's not possible, right? Even if you take a small amount of time will take, right, for sure. There is a very small time which will take. As soon as you say that, okay, there is a pulse width, then that is not delta. That's why I'm saying it is not possible to generate, right? So which means, so far whatever we discuss, okay, I use a delta function, impulse train, I have given an equation for that, I try to sample it out, right, etc. Whatever we discussed so far, right, that is going to be the ideal case only. It's not practical. So that's why I wrote a first sentence here. So far the sampling, whatever we consider, it's an ideal case, right? So the ideal, right? So the ideal circuit should look like this. Okay, let's see. So here we have the input signal coming. Let's write that is g of t. All right. Now, uh, let's consider this to be the ground, in the sense of 0 volts. All right. If I have this portion of the circuit to be a sampler, this actually oscillates between, this keeps touching, right, one of them at a given point of time. Whenever you want to sample, you bring it and make it to touch this, the g of t line, so that that value will be passed on to the output. Okay, so when that means the output that comes here is the sampled version g delta of t. According to our notation, this is what this is what is happening. All right, so g of t comes, you sample it at a given point of time. In the sense, it should, the point should touch this, right? The line, the arrowhead should touch. Okay, I'll write, I'll give a name here so that we can trace it out which point it is touching at what point of time. Okay, so this is what I want to denote it as 1. This is a point number 2. So arrowhead should touch point number 1, right, for no duration, only that it should touch. So what is the width of that pulse it touches? It should touch 0, right? Right, only at t equal to 0 it can touch. It cannot touch even at 0.00000001, right? It's not valid, right? It should touch only for, right, only one instant. That is not possible. That's not going to happen, right? It will definitely touch for some time. That means it is not ideal. It's a practical case, right? So now we are going to look at the practical case. This is an ideal sampler, right? So sampling of a strictly band limited signal using the Dirac-Coombe, right, here. So let me try to write the one sentence about that. What do you mean when we say that ideal sampling? So far whatever we discussed is completely ideal sampling only, but we never discussed about this aspect. Okay, so here we sample a band limited signal, that is g of t, by a Dirac-Coombe function. So this implies, when I say Dirac-Coombe implies, the switch which we are considering here. So there is a switch S, right? So the switch S remains at position 1, right? How much? What's the duration? It remains at position 1 for a time duration equal to almost 0. Immediately it should move back to, right, 2. Right. So the time it remains at 2 each is very, very greater, much greater than the time it remains at 1. That's what is expected, correct? Normally you see it touches 1, then comes back to 2, holds on, it remains at 2 for a long time, again goes back, touches 1, comes back. But the touching of 1 happens for a duration that is equal to 0. That is very important when it comes to the concept of the sampling, right? Sampling, the sampling time. right? So which remains at position 1 for a time I can say equal to 0, right? It should remain there only for 0 seconds, right? Exactly 0, no extension, not an approximation, right? Equal to 0, and then moves back to the position number 2, right? And what's the duration? It remains at 2. It remains there for the remaining duration, that is the sampling duration, that is equal to ts. Okay, and I can write it remains there for, okay, I can write for a time equal to, let's write in that way, that makes more sense. For time equal to the sampling duration denoted by capital Ts. Do you agree? Right? So it will touch, it will come back, it will stay there for Ts. Next, once again, moves back, touches that, comes back. This is what the ideal case we discussed so far. Right? It is impossible to even imagine that there is such a high speed switching, right? Possible even using the most sophisticated VLSI circuit that implements very high speed, whatever we can think of, right? Very high speed, maybe uh, the FETs possibly, right? That cannot do this job. It is impossible, right? So now I come to the actual problem, right? So that is my next point will justify what I'm saying. So such switch is impossible to realize using the high speed high speed switching. Now, nowadays, everything is CMOS, complementary MOS logic. You might have studied in the VLSI circuits or something. Okay, so high speed switching CMOS circuits. It's not possible to realize. So the right problem is that you have to find a switch that remains in position 1 for a length of time that is equal to close to 0. Okay, so what we try to do here, right? The practical scenario is that uh, instead of assuming that the switch is going to remain there at till time t is equal to 0 seconds, you can assume that you give it time, you give some time for the circuit, right? To remain there at position 1. It remains at position 1 for some duration, right? It takes some time t, right? So this is what is the practical scenario now. So I'll write one more point here. So okay, the problem being to find a switch that remains at position 1 for time duration equal to 0. This is the problem, right? So we give the solution now. In practice, we select a switch which is allowed to remain at position 1 for a small duration, right? T. Now you see that this T in bracket L, right? The T will be much smaller compared to the sampling duration. This is still true. Okay, previously we were expecting that this capital T was 0, right? It's not expected to remain there for a larger duration, but now anyway we understood that the actual practical implementation of the delta function is not possible. So that means now we are making an assumption. So instead of this function, you are trying to make sure that you will allow a very small time duration. So, so you are allowing a small time interval between this. So make sure that, right? So this is the capital T. Okay. Now, because of this, now you have a small width available, correct? So we will find that the samples of an analog signal, right? The samples are not of duration 0. They have a small, what you call length associated with them. Okay. This means let's consider the. Okay, let me say I'll write both the functions what we are expecting and what we really get. So let me say that. Okay, let me take. Okay, this is our analog function or the continuous function. Okay, this is x of t, and let me say this is my function. Possible. Okay, I'll copy this and I need the same thing to be applicated for. So this is what I'm expecting when I say that I'm trying to, I go for ideal sampling, right? So when you see you are doing the ideal sampling, right? I know that I'm trying to sample at equal intervals of time. One here, maybe one more here. The third one is this. Maybe, okay, I'm giving 1, 2, 3, 4, 5. Okay. So let's say I'm giving a gap of 5 duration. 1, 2, 3, 4, 5. 1, 2, 4, 5. Okay. One comes here. Okay. Possibly something like this. Whatever the red dots we can see, right? They correspond to the sampled versions. Ideal sampling gives you only these points, right? And I know that I can denote them by using this. Okay, so that means this is my next sample. So the gap between them is Ts, the sampling duration, and you see the width of every delta functions we wrote right here is 0. So that makes the whole concept as a ideal concept, right? Only it remains only in the mathematics, not in the practice. Okay, so okay, let's complete them quickly. The next one, next one, and one more. Okay, so this is how the practical, sorry, the ideal sampling looks like. Right, now we'll come to the practical one. There is a width associated with each of the pulse. We have a small amount of width associated with that. So this is, I'll just write this is x delta of t. Okay, so that we understand that using the delta function, we sampled it out. Okay, so this is some x delta of t. So what I do, I'll write the practical version over here. Okay, now the same positions will do the sampling, but you see the sampling happens with not just with okay, I need two straight lines. I'll change the color. So let me go back to the red. Now, so the sample actually begins over here. Since there is a small width allowed for sampling, this will sample, say, maybe for one complete thing. So you see, your samples will look like this now. So whatever the red you see, right, that is the complete sample. So sample will hold for some duration. In a sense, it will sample everything during that time interval, right? So you see the red will follow the given pulse, right? So assuming that this is my next sample, that actually happens over here. Now you see, it will follow the amplitude, right? In the sense, whatever the amplitude, right, the function takes during that small duration capital T, that will be shown even on the sampled signal. That's what is my point. Okay. So anyway, later on I'll erase the original signal to justify this. So it actually begins somewhere here, and it will, so it will actually begin from the same point, and it will come down. So you see the function will hold on to this, will take up all the values. So whatever value we see there, right, it will be present even on the sample signal. You see like this, right? Like this, it right samples out all. In every sample, you'll see the magnitude being changed. Magnitude change that originally represent the change of the magnitude of your continuous signal during that time duration, like this. So this is the one. Let me assume that I have sampled it till here. So that is a pulse width. And during this width, whatever change that you see in the pulse amplitude, that will be retained. So over there at the top, I can see that, right, there's a change in the amplitude that will be retained. So like this. Next sample, maybe I'll write a few more samples so that we can clearly see what is happening. Okay, maybe this is the next point where we do the sampling. But because of the width, this is the width, and I can see that there's a amplitude like this. Then we have another pulse over here, and that is also going to show a change of amplitude like this. Okay, now what we do, we consider both waveforms, and so using both the waveforms, we'll try to make a comparison so that it becomes very clear for us. So before that, let me try to erase the unwanted part of signals. So compare this with the older one, wherein you can see that ideally speaking, we should get only those dots, right, which are the samples corresponding to the sampling that instant, right? Very at the very moment, whatever amplitude, right, we had in the original signal should be coming at the output. This is what we expect. That is x delta of t. Now we don't get that. Okay. Now, so now if you see, we are getting something completely different, right? Which is not at all what we expect. So let's try to call it by a different name. So this is what we expected, right? So x delta of t was the name which we tried to give there. Now I'll call this as say it's actually the practical version of the function. Okay, the practical value we obtain after we sample this. Okay, so let's try to call it as say some other name. Okay, let's call it as some s of t, the sample signal s of t. Right. Now, the idea here is like the sampling occurs still at Ts. So let's try to denote the time duration. So this gap is still Ts. Okay. Every gap is Ts. Like I may have 0, first sample is Ts, 2 Ts, 3 Ts, 4 Ts, and so on. The same thing will be, right, happening here. So this is 0. The now you see there is a small width of the pulse. So what is that width? You know that it is denoted as capital T now. So this width is capital T, but the pulse is still assumed to be located, the central value of the pulse, whatever you see at the center, right? The midpoint of the pulse is still Ts, assumed to be Ts. Okay, so Ts, 2 Ts, 3 Ts, and so on. This is 4 Ts, but the width of the pulse is T. So I have 5 Ts at the center. Are you okay? So I have to maintain the TS, right? It is still going to, right, maintain the periodicity. The period is capital TS, which is used to sample. Okay, so that means the samples of analog signal are actually lengthened. There is a length associated with that, that is equal to capital T. All right. So this is, now this actually is a practical case because this can be implemented by using our high speed switches implementation by using any of the maybe CMOS logic, right, or simple N MOSFETs, P MOSFETs, or anything, right? Even the BJTs can be used to implement this. Okay. So practical sampling is going to be like this. So we try to make a comparison of what is ideally, right, we were thinking we are going to do, but that is impossible to do that. So we will be doing this in the practical sampling or the natural sampling, right? Okay, so let me write one more point here. So here the samples of the analog signal samples, okay, are lengthened. You do this intentionally, right? We give a pulse width over there because we have some intention behind that, right? Practical case is impossible. This is the uh, sorry, ideal case is impossible. This is the practical case. That's why intentionally you allow. Okay, so this results in what is called as the natural sampling, right? You see the nature, whatever is existing in case of your whatever amplitude changes that naturally exists in the x of t is carried as it is, right? Whatever it exists over there, you carry as it is. The natural amplitude of your signal is retained in your sample. That's why the name given here is natural sample. You try to keep the changes in the amplitude as it is, right, for certain duration of time. Okay, so that's what is considered as natural sampling. So now, so now in natural sampling, what happens? We'll try to write that in. So in case of the natural sampling, we know that uh, so the sample circuit we cannot change it, right? The circuit still remains same. You can even write the same circuit which we wrote earlier for sampling, but in the explanation you will say that, right, the switch will move to position 1 for certain duration capital T, and it comes back and remains there for the remaining amount of TS. That's how it is. Okay. So, okay, let's try to write it in this way. So, in case of the natural sampling, the switch, same switch S moves from which position to position. So normally position 1 to position 2, it moves with a particular rate. That is the sampling rate. Okay, so sampling rate is predefined, that is denoted by uh, TS. Sorry, rate means it should be 1 by TS. Okay, so moves from, right, position 1 to position 2 at a rate means it is frequency. Fs is equal to 1 divided by Ts, right? So at that rate, so many per second, right? At that rate, it will keep moving. And in addition to that, we have to satisfy another condition. So what is that condition? The condition is that it should remain at position 1 for a very small interval of time. Okay, and it remains in position 1 for a small interval of time equal to t seconds, right? So that is the practical aspect of the sampling. Now let us try to visualize this in a different way, right? We want to visualize this in a different way. So what we do now, okay, let's say what are the various aspects we have here. So if I try to visualize this whole process as a multiplication, right? So let's try to consider that now. So that's the other view of the whole process, right? So I can write considering this in the sense it's the practical, okay, considering this sampling as multiplication. Why we are trying to bring the concept of multiplication here? Because everything we studied so far was a multiplication, right? So in the sense you had a signal multiplied by the Dirac-Coombe function to get the result, right, of the sampling. Now I want to do the bring the same analogy over here. That's why we are considering this to be the multiplication process. So let's try to visualize that. I have the signal g of t coming here. This is the input signal. Give it to a multiplier. So take another input to the multiplier. That is now it's not going to be the delta function. This is some other function. So I'll call that as a sampling function. What is that? Okay, I already give a g of t over there. So let's try to change the name. Instead of g of t, I'll call this as a function, say c of t. So we have the output. I think I gave a name s of t over there. So s of t is equal to, it's a simple multiplication, g of t with the c of t. Right. Now let us look at the c of t, right? Where the c of t is a sampling function, sampling waveform with the period capital Th. Okay, so let me write that point as well so that this becomes clear when you read again. So that means where c of t is the sampling waveform of period equal to capital Ts. So let's try to give a pictorial representation of the same thing. So far we never discussed that. We just mentioned that, okay, this is how it's going to look like a rectangular pulse, but now we are giving the actual representation. Okay, so this is how the waveform is going to look like. So it's a small pulse. So whatever amplitude we want, we can assume. Okay, and let me try to. Okay, let me write it here. So let me assume that this is same pulse, and I'll write another pulse on the other side. Okay, so that okay now. So if I at the center this is 0, what is this point? So because I know that the width of the pulse is uh, totally the width is capital T, right? So on one side this point should be T by 2, and even on the other side there should be a value minus of T by 2, so that the what is the total width I can write here till here, the value should be equal to capital T. So width still remains T by 2 minus T by 2, so that is equal to, right, capital T. So the width of the pulse is capital T now, as we discussed earlier. So this value will be held true for each and every sample that each and every pulse that we have here. So I can write this to be the capital T, right? Once again, I have the similar width over here, that is also capital T. So you can see that this is capital T and so on. So this is the waveform C of t. I have to write this central point is Ts. This central point is minus Ts and so on. So this is going to be repeated now all the way from minus infinity to plus infinity. So this is the practically used waveform for sampling as a sampling function. Okay, now now we have a question here. Okay, so by using what is called as the ideal sampling, that means the Dirac-Coombe function, we could justify that yes, you can try to represent any given function, right, any given analog function as a sample, and you can come back. Both were possible, correct? So if you remember, we proved that okay, if you use a Dirac-Coombe function to sample, yes, you can sample it out, and you can come back, right? You can reconstruct your original signal from that. Okay, this is what uh, resulted as a part of our discussion we had considering the ideal sampling so far. But now I have the same question coming back once again. Are the sampled segments using these natural sampling, right, are those samples capable of representing your original signal? This is the first thing, right? Once you can say that yes, they can be considered as the samples of your original signal, right? I have a second question coming up. If yes, then how do you reconstruct? In the sense, when you reconstruct, will you get your original signal back? Those are the two questions which we need to answer, right? Whenever we change our sampling function from Dirac-Coombe into this naturally, uh, we can call this as a natural sampling function.